Okay, we continue. Microcontroller and software.
This lecture, we'll talk about microcontrollers in a little bit more detail. Specifically, we're going to talk about the storage elements and how you store data inside a microcontroller. Some of this is important for us just to have an idea of what type of elements there are inside a microcontroller. And not just inside a microcontroller, really, but also the memories outside the microcontroller, because these are important parts of the system. Right? You always have data, you need to store it. So we need to know a little bit about that. So first, here's a picture of taken out of a data sheet for an AVR Atmega 2560 microcontroller. This Atmega 2560 is not the same as what's in the Arduino, but it's no, not in the regular Arduino. The Arduino Uno, it doesn't have this. Actually, I think there is an Arduino that uses one of these, but this is the same series of processes you find in an Arduino. And here's some of the information you would find right on the front page of the data sheet: 8-bit microcontroller, up to 16 megahertz. That's the clock frequency. 256 kilobytes of flash memory, so that tells you something about the type of memory in there. Flash memory, as you may know, is a type of memory that it's non-volatile memory. So after you lose power, when you regain power, the memory is still there. So you see this in thumb drives. Thumb drives are basically flash memory. EEPROM is also another type of non-volatile memory, similar to flash. SRAM is your regular random access memory. We'll talk about that. And then peripherals are that's sort of a general term for all the other components inside the microcontroller on the chip, like the timers, A to D converters, and all those other things. So it's got a number of peripherals that I didn't list. I didn't put the whole data sheet up there. But that picture right there shows you what kind of what the pins look like. So actually where they are configured on the chip. So that means if you bought the chip, then which pin corresponds to which function, and they're all labeled right there. Actually, this is just a snippet of it because we couldn't put all the pins on this one page. But this is like the upper left-hand corner of the chip. It shows you the pins that you can see there, and there are a lot more pins than that. But they're all labeled with names that are referred to later in the data sheet. So let's talk a little bit about storage elements you find in these microcontrollers. Storage elements are basically elements that store data, and there's a need for a lot of data, so you need to store data. A variety of types of different data. You can store data, you can store the program itself. The program itself is data, right? So that has to be stored in some sort of storage element as well. And there are different types of storage elements. There's a speed-performance trade-off. So some types of storage are very fast, but they cost more. Usually they cost more because of area. They take up a lot more area on the chip, so they cost more. Or on the other hand, there are other types of storage elements that are slower to access, but they cost less. They're much smaller on the chip. There's also a power trade-off that I didn't mention here. So, most basic storage element, fastest storage element is a register. A register, it stores only a single value. Now, depending on how many bits and wide the register is, it stores one number. So if you have a 32-bit data path, you'll typically have 32-bit registers. So it can store one 32-bit number. It might be a stores whatever you want, one 32-bit number, maybe the location in a certain memory location, the value in a memory location, or some number that you're working with, some variable you're working with right now in the program, something like that. Very fast. So when I say very fast, the access time is a lot less than a clock cycle. But it's expensive, so you can't have too many of them on chip because they're so big. So there's several special purpose registers that are devoted to particular tasks on the microcontroller. Like the program counter is a common one. Program counter is the register that tells you what instruction you're executing in the code. It's the address of the instruction you're currently executing. So that's something that you, as a programmer, shouldn't be manipulating, shouldn't be touching that. But it's a special purpose register. But there are also a set of general purpose registers that your program can actually use for computation, arithmetic, things like that. There's also a register file. A register file is basically a group of registers put together. So these are commonly how registers are organized inside microcontrollers. It acts like a memory, just a very fast memory, right? You can only read one or two of these registers at the same time, but usually you don't need to read more than two in a particular clock cycle. Their instruction operands are stored inside register files. So what you're seeing there is an add instruction. Add R1 or 2 or 3 or 3 R1. It's not going to look like that to you. That's what the machine is actually running. The simple instructions that the machine is actually executing. We'll talk about that a little bit later. But notice it has these operands. So R3 is a destination register. That's the name of register R3. And R2 and R1 are the two source operands, the two things that want to get added together. So what this instruction does, it takes the contents of register R1, contents of register R2, adds them together, puts the results in register R3. So commonly these microcontrollers are reading data out of registers, putting results into registers because they're fast. You want to work with registers all the time if you can. You can only read one or two at a time. And you can contain, typically the register file often has like say 32 registers. That's very common to find in a microcontroller, 32 different registers that you can access. So that gives you a hint as to how expensive they are. 32 isn't much, but that's generally all you can afford on a microcontroller. Memories. Now memories are, you know what a memory is, it stores data, but memories are made to store a lot more data than registers. So you won't just have 32 registers. Memories will be a lot bigger. So there are varieties of memory. One type of memory is called cache memory. Cache memory, it stores a lot of values. I just gave you a ballpark on how big a cache typically is. This is all ballpark for right now, but let's say, modern processor, maybe you got a 1 megahertz cache. 1 megahertz, 1 megabit cache. That's ballpark, but say you got a 1 megabit cache, and that can be plus or minus. But that tells you something about how big they typically are. So usually they're a lot bigger than register files, but they're also slower than register files. Where a register file, you can access that in a fraction of a clock cycle. A cache typically takes you a clock cycle to access, a full clock cycle, which is pretty good, but not as good as a register file. Still fast and expensive. They're cheaper than register files, but they're more expensive than larger memories. So that's a cache, and that's on chip. You would find that on the same integrated circuit as the microcontroller. Commonly in microcontrollers, we're using what's called a Harvard architecture. So you have two different caches, at least two. You'll have a data cache and an instruction cache. The data cache holds the data that the program is operating on, and the instruction cache holds the actual instructions of the code that's being executed. So it's common to separate those two. Now then there's also main memory. Main memory is like cache, except it's bigger and cheaper and slower. So you can see the pictures right there of main memory. That's a typical main memory. If you've ever taken your computer and installed memory into your desktop, you'll get something that looks like what we see in the picture, and you can plug it into a slot inside the board. So it's very big, gigabytes of memory, not in the CPU. So it's not on the same chip as the bytes. Oh, by the way, CPU again. I'm throwing another term. By CPU, I'm using that the same as a microprocessor and the same as a microcontroller. Okay, same thing roughly. So main memory is not going to be in the CPU. It's off the CPU. It's on the same board, but it's on a different chip, different set of chips. In fact, if you look at that memory, it's multiple chips, right, all put together. It connects to the system, connects the CPU via a system bus. So the system bus is basically a group of wires that are basically drawn onto the circuit board, the printed circuit board, that connect the main microcontroller to the memories. Memory access is slow relative to the cache. So what that means is that in a cache, you might be able to access a cache in one clock cycle, right? And main memory, maybe you have to wait 100 clock cycles to access main memory. So that, again, that's ballpark, but that's not unrealistic at all. There's what's called the von Neumann bottleneck, which is the fact that in a von Neumann architecture, the data and the instruction are all put into the main memory, and the problem is that main memory is much slower than the processor. So main memory, like I say, maybe you wait 100 clock cycles to access something out of main memory. So if you say you want to do an add instruction, you want to add two pieces of data that are in main memory, you're waiting 100 clock cycles for that data to show up, and then the add itself takes one clock cycle. So all your time is going into memory accesses, right? Or can go into memory accesses, and that is why people use caches. So that to avoid this von Neumann bottleneck. So the von Neumann bottleneck is a bottleneck to accessing main memory. It's the fact that the memory is much slower than the processor. So to avoid that, you basically use the cache. You try to rely on the cache and the registers as much as you can, so that you don't have to go to main memory. Now, all these complexities that I'm talking about are you accessing cache, the register, the main memory? A lot of these we will not be dealing with in this class because we'll be writing code in either C or in Python. And so all these details about where the memory, where the data is going to be, is this register going to contain this variable, or is it the variable going to be in cache or main memory? All those issues are dealt with by the compiler if it's C, C++, or the interpreter if it's say Python. So we are not going to have to worry about this level of detail as much, but it's important to understand the difference in the different types of storage elements and how they act and how fast they are, how slow they are, so on. Thank you.
Compilation and interpretation.
This lecture will talk about the software side a little bit, specifically how the software is processed before it's actually executed in the microcontroller. So key here is that the code that you actually write isn't literally processed by the microcontroller. It's not executed directly. It has to be processed first, compiled or interpreted, and then it's processed. So we'll talk about that. Software translation. So in the end, a microcontroller, or CPU as we're calling it right here, microcontroller, it doesn't understand C or C++ or Java or Python or any of those languages that most humans program in. It understands its own machine language. So so take an Intel processor. It understands Intel machine language, x86 machine language it's called. So different processor families understand their own machine language. Now machine language is basically a set of really small, simple instructions encoded in binary, zeros and ones. So if you ever look at machine code directly, all you see are zeros and ones. Or typically people, when they view it, they look at it in a hex editor. So they see zeros and ones represented in hexadecimal. So, but it doesn't look too readable. Basically, it's a string of characters, 0 through 9 and A through F, right? And you just see them in pairs. So it's not easily readable, but that's what the machine actually executes. It's machine code, which is an encoding of very simple instructions: add, subtract, multiply, very basic instructions. Now, above that is what's called assembly language. Now, assembly language is basically a one-to-one mapping from the machine code that's actually executed to a mnemonic, a simple mnemonic that a human can read. And now it's not easy to read, but it's easier than the zeros and ones. So instead of having a sequence of zeros and one, assembly code will say add, R1, R2, R3, something like that. So that's readable. But still, it's very low level. These instructions are very simple. You can't have for loops or any of the common constructs that you have in programming languages. You can't use any of that. These are very simple instructions. So assembly language to machine language, they are one-to-one mapping, right? You have an assembly instruction. It is exactly equal to a machine language instruction. So it's very simple, but at least it's readable. It's in some sort of English-like format. So you can write an assembly language, but it's hard, and we're certainly not doing it in this class. People do it sometimes for certain purposes, but we're not doing it in this class. What we work with are high-level languages, what we'll call high-level languages. The commonly used languages, C, C++, Java, Python, which is what we're going to look at. We'll focus on C, C++, and Python, but there are many high-level languages that people program in. So these are much easier to use. They give you the regular programming constructs that programs are used to, loop constructs, variables, structures, objects, things like this. So those languages, high-level languages, are what we're actually going to code in. But that's not what's actually executed. The machine language is what's actually executed. So this high-level code, high-level language that you write in, it has to be converted into machine language before execution. So all the software that you write in a high-level language has to be translated into machine language, into the machine language of the microcontroller before you can actually execute it. So there's always that process. You're going to write the code, then you're going to do the translation, and then it gets executed. Now, there are two ways this can go, depending on if it's compiled language or an interpreted language. So compiled language, what happens is compilation happens where the language, the instructions get translated into machine code before execution one time. And you get what's called an executable at the end, which is basically the machine code, and plus some extra data, but essentially machine code. And this executable is what is run every time you run the code. So the compilation, the translation from the high-level language to the machine code happened one time before you executed it. And then every time you execute it after that, you don't have to do that conversion. Okay? So compiled languages include C, C++, Java, halfway. There are other languages too. They're compiled languages. So when we work the Arduino, we'll be working in C++ essentially. So that's a compiled language. So this translation, this compilation process happens once. Realistically, it happens many times because you compile it and then you realize you had a bug and you fix it, compile again. But essentially, you finish compiling it, and once you're done and it works, then you never compile it again. You just execute it. Okay? Now, as compared to compilation, there's also interpretation. So you can have an interpreted language, like Java, Basic, Visual Basic. Python is an interpreted language, or a scripting language, but also interpreted language. So in interpreted language, what happens is the instructions, the Python instructions, let's say, are converted into machine code at runtime. So every time you execute that code, you have to convert the Python into machine code. Unlike with the compiled language, right? Compiled language, you compiled it once and you got the machine code, and then every time you executed it, you didn't have to compile again. But with interpreted languages, you have to compile every single time. Or you call it interpretation, but it's the same thing. You have to convert into machine code every single time. Now, there are advantages and disadvantages. The disadvantage is that it's slow. Compared to compiled code, it's slow because you have to do that whole conversion from high level to low level every single time. But it has a lot of advantages because it allows you, as a programmer, it relieves you of certain burdens. So certain things the programmer doesn't have to think of because the interpreter will deal with them. So for instance, just as an example, let's say in C, you're using a variable, you're trying a variable, integer. In C, if you want to use an integer, you have to declare that integer. You have to say int x, let's say. And you have to put that at the top of your code so the compiler can know he needs an integer x, right? And with an interpreter, like with the Python language, you don't have to declare x as an integer. You can just start using a variable called x. And the interpreter will figure out, oh, I think he means for this to be an integer. I'll refer to this as an integer. Or if it sees you're using the variable differently, it'll make it a floating point or something like that. But that's a burden that the programmer no longer has to deal with, right? The interpreter at runtime can figure out what the type is rather than you as a programmer have to deal with it. So interpreted languages do have the advantage that they are generally easier to program in, but they are slow. Thank you.
Python versus C++.
So this lecture will talk about comparison between Python and C, C++, because Python is what we're going to be using with the Raspberry Pi, C, C++ we'll be using with the Arduino. Also, we'll talk a little bit more detail just to understand the contrast. We'll talk about the tool chain, the software tool chain, all the tools that go into taking a high-level piece of code and getting the eventual machine code. We'll just look at that whole picture because it ends up looking a little bit different for one versus the other. So Python is an interpreted language. It's a scripting language, but that's also an interpreted language. It's high-level language. It's easier to work with because it's interpreted. So there's certain things the program does not have to deal with, like the type of variables. Is it an integer? Is it a floating point? Is it a string? You don't have to worry about that in Python. Python figures that all out based on how you use the code, how you use the variable. So at runtime, while it's executing and doing the interpretation, it can figure that out. Other things too, like memory management. In C, C++, you have to deal with that. You have to say, look, I need more space. There's a function called malloc. You can allocate more space. I need more memory for this variable. Python, you don't have to say that. It'll just make it for you, right? And when you're done with it, it'll get rid of it. So when you're in C, you have to make it explicitly, and you have to, as a programmer, have to know, oh, now I'm done with it. Let me free that memory. So there are a lot of these burdens, these programming burdens that you don't have to deal with in a language like Python because the interpreter is there to take care of it for you at runtime. Now, comparing that to C, C++, C and C++, they're related languages. Actually, C is a subset of C++. So C came first. C++ came second. C++ is a superset. So C++ does everything that C does. So if you have a C compiler, a C++ compiler, it'll compile any C code. But C and C++ are compiled languages. So you write the code, you compile it once, and then you get an executable, which is machine code plus extra information, and you only execute the machine code. You don't have to do the interpretation at runtime. So as a result, C programs are generally a lot faster than Python programs, but the programmer has to deal with a lot more details. Now, dealing with a lot of details is hard, but when it comes to embedded systems, it's often useful because sometimes, not just sometimes, often, the programmer, an intelligent programmer, can write code more efficiently than the Python interpreter can. Okay? So the programmer, knowing something about the behavior, what the behavior they expect, they can write their C++ code in such a way that it runs a lot faster than the Python interpreter could ever predict. Because the Python interpreter, it's dumb compared to a human, right? A human can know something more about the context in which the software is being used. So C and C++ are commonly used in embedded systems. Outside of embedded systems, you see them used less. Maybe Java is favored or something like that. But because of the level of control you get with C, they're much more commonly used in embedded systems. So compilation, this is what compilation looks like roughly. At the top, you've got, say, some regular C code. And actually, that code's pretty generic. You can have A plus B plus C in any number of languages. Java, Python, they look all very similar, except for the semicolon at the end, that could have been Python. Right? So you've got your high-level language at the top. And in the end, you want to get what you see at the bottom, a sequence of zeros and ones that represent the instructions. So what happens is if you look at the top instruction, it's actually broken down into a set of smaller steps, smaller behaviors. So that instruction, A equals B plus C, that actually, it's not just an add instruction. It's not just an add that will be performed. First, you got to get the B variable, you got to get the C variable, you got to add, and then you got to put the result back. So maybe B and C are in memory somewhere, and A has to go to memory. So first, you got to load A from memory, or load B from memory rather, then load C from memory, then do the add, then store the result back in memory for A. And that's why you got 4 instructions in there in the middle. You got 4 what you call assembly instructions. So the compiler will make assembly instructions. The load LW is load words. It'll load B into memory. Then the next LW loads C into memory, and specifically into registers R1 and R2. Then the add takes R1 and R2, adds them, puts the results in R3, and then the last instruction SW store word that takes what's in R3 and puts that back into memory wherever you want A to go. So that one high-level instruction breaks down to 4 simpler assembly level instructions, and then the assembler takes each one of those 4 instructions and converts it into sequence of zeros and ones. So you can see at the bottom you see actually 1 instruction, just the add instruction, but presumably you have 4 instructions, 4 sequences of 0 and 1s, just like that, to correspond to each one of the 4 assembly instructions. So that's the process of compilation, a very simple version of it. But you take a high-level language, in the end you get a sequence of zeros and ones that represents the instructions that need to be performed, and those zeros and ones are what get interpreted by the microcontroller. So this is a high-level view of your standard tool chain, software tool chain. A tool chain is basically a term that's used in embedded systems a lot and in IoT devices a lot that describes the sequence of tools, of software tools that you have to use in order to convert a program that you code into an executable program on the platform. So if you look at this picture, we start off with the host up at the top left. The host is laptop, desktop, whatever it is, you're actually writing the code on. So you write your code on the host using some text editor, it doesn't really matter which one. Then this is actually a compile tool chain. So you write your code, let's assume it's C. The C code comes out of the host, it goes into a compiler. So the compiler, actually I should have said here, this is what's called a cross compiler. So a cross compiler is a compiler that takes the C code and converts it into assembly code. Okay? But the assembly code is for the target platform. So the target platform is whatever microprocessor you're targeting. So let's say I'm using an Arduino, right? The processor on there is going to be an AVR at megaprocessor. So the compiler is a cross compiler. It'll compile and make assembly code that works for that AVR at megaprocessor. So the compiler makes that. Then that code goes into an assembler and gets an object file is generated, which is actually machine code, okay? For the target platform, for the AVR at mega, whatever it is. So the OBJ file, the object file, that has the machine code plus extra debugging information, other sort of information in there, but it has the machine code. Now you'll notice that there's a path on the top from the host into the assembler, assembly code. You could write assembly code directly. So you could write C code, which is what we'll do. You could also write assembly code directly. We will not do that, but you could, and that would get merged in at the assembly phase. So then once you get the object file still, that describes all the code that you wrote. But remember that we're using library functions all the time, and we haven't done this yet, but in our code, you always want to use library functions to handle complicated tasks. Now library functions are really just functions that are pre-written, but you didn't write them. You just call the function, you just write the name of the function, and that code gets executed. So all those library functions have to get integrated into your program at some point, and that's what the linker does. So the linker, we don't see this in the picture, but the linker, it has access to all the libraries. And the linker basically takes the library's code and inserts it into your code at the appropriate place. It creates links between your code and the library code that you use. And then the output of the linker is going to be some executable program. Now, the standard path that we're going to use is from the linker to the programmer, which then goes to the microprocessor. So the programmer, what that does is it takes the executable code and copies it, writes it from the host machine onto the microprocessor, usually into the flash memory of the microprocessor. Because in order for the microprocessor to actually execute the code has to be sitting on its memory. So that's what the programmer does, and that actually goes on via USB cable for us, right? And the programmer will take the code, send it across the USB cable, and write it into the target, say Arduino for us or Raspberry Pi or whatever it is. So that's the programmer. There can also be another path, a debugging path, where if you're using a debugger, which is a little more sophisticated than what we're going to deal with, you can take the executable and write it into the target platform and write debug code in there too, and control it during execution. You can set breakpoints, things like that. We won't cover that right now. Thank you.
Operating system.
This lecture will talk about operating systems a little bit, what an operating system is. Now, they're not always present in IoT devices, and in fact, with the platforms we'll be working with an Arduino and a Raspberry Pi. With an Arduino, you do not have an operating system. It's really too slow to support that, but Raspberry Pi you do, typically. So we'll talk about the role of an operating system in an embedded system and an IoT device. You may or may not need it. So an operating system is an extra layer in between the program, your application code, and the actual hardware. So generally, say we're working on an Arduino, right? There's a user at the top who's using some application, right? And this application, by application we mean the actual program, right? So you've compiled the program, and that application, that's the application code. Now, if it were an Arduino, that application code would connect directly to the hardware. So it would go straight from the application to the hardware, no operating system at all. And the application directly controls the hardware, sets signals high and low, and so on. But in, say, Raspberry Pi or a more complicated IoT device, you would have something like what you see here, where the user talks to the application code actually may not directly connect to the hardware, it communicates with the operating system. So it makes calls from the operating system and requesting hardware service, and the operating system manages the hardware most directly. So that's where an operating system fits in the picture, that the code that you write and compile, the application code, that interfaces with the operating system, and the operating system deals with the details of interacting with the hardware. So it manages other programs. So one thing about an operating system is that it allows you to not have not only one application, but many applications. So you can run lots of different applications at one time, and the operating system itself manages the hardware. So it gives them turns, lets them take turns, and stuff like that. And you see this in standard operating systems like Windows or in iOS or something like that. You run, typically on a laptop, desktop, you run many programs at one time, and the operating system allows you to do that, right? Without an operating system, you can only run one program at a time. So you can execute a lot of programs together, and when you're executing together, remember, they're not actually executing together, they just seem like it. So it's really alternating, but very fast, faster than a human would really notice. So it looks like they're all running at the same time. Nice user interface. So often, now how nice user interface really depends on the operating system. If you look at a desktop or laptop, Windows, iOS, Linux, something like that, they will have a very nice user interface. You know, graphic user interface, GUI. You can double click on something, double click on a file, it'll open it up, that sort of thing. That's a full-on operating system. The operating systems that you find in an IoT device, they're much smaller and stripped back. So they're not likely to have any graphical user interface or anything like that, but they will have a user interface, a command line. So if you ever use a Windows command line prompt, or iOS use a terminal window, Linux use a terminal window, something like that, that's, I call that a nice user interface. It's text-based, but it's nicer than not having it. So there's a user interface that's provided of some kind. And it needs processing power. So one thing about operating systems is that the operating system itself is a big program, right? It's a big program that's running in addition to the actual programs that you want to run on your IoT device. So it's going to consume clock cycles, right? There are some clock cycles that are spent doing operating system tasks, right? Some memory that's spent storing the operating system data, things like this. So the operating system itself takes up resources. So you have to make a decision as to whether you need one or not, because it's going to cost you resources, which means cost you money. It slows down the system because the operating system, while the processor is working on the operating system, executing the operating system code, it can't be executing your actual application. So it slows things down. And so as a result, when you use an operating system, you generally need a faster processor. That's why if you look at an Arduino, which is running maybe 8 megahertz, something like that, you usually don't support an operating system with that. But if you run a Raspberry Pi, you've got like 1 gigahertz, then it's okay to support an operating system because it has enough clock cycles that you can do that. A little example of an operating system that I had a student group do something like this, do a project like this several years ago, where they wanted to have a web control car with a camera. So it's an RC car controlled through the web. So you can go to a laptop, desktop, whatever, anything has Wi-Fi. You can go to a phone, open up a browser, and connect to the car. And the car has on it a camera and its own web server, right? So you can connect to its web server and control the car through its own web server. So it has an interface that looks roughly like what you're seeing down here. On one side, there's a picture, the image of what the car sees. So that's actually coming from the car's camera. So like I said, the car on it had a camera, it was connected to a web server. So the view from the camera would be streamed through Wi-Fi over to whatever your browser device is, right? Then it would have buttons forward, back, left, right to control the car. So you click forward and move the car forward, click back and move back, and so on. So you can send commands to drive the car through Wi-Fi to its web server, to the car's web server, and then that would directly control the steering and the motors and all that. So in a system like this, it's useful to have an operating system because there's so many things going on at one time. So the car's controlled over the internet, Wi-Fi generally. The car has its own web server, which has a URL address. And the web interface allows you to control the car and see the images and so on. Also has an auto brake feature to avoid collisions, so it'll stop automatically regardless of what your controls are. If it senses something in front of it, it'll stop. But the idea is that it generally has a lot of tasks to do, a lot of things to do at one time, and in that type of situation, an operating system can be very useful. Thank you.
Start support.
So this lecture, we'll talk about a little more about operating systems and what they do. We'll talk about task and process support, really, about how operating systems support multiple tasks executing at the same time, and how it's useful in certain IoT devices, in more complicated IoT devices. So multiple tasks. So this is actually going back to the last lecture where we were talking about this embedded system that I had my students make. Actually, IoT device was a web controlled car, and through the internet, you could go to a browser, open up a browser, and remotely control this car. So you could view what its camera was seeing on your web browser. Also, you could hit some buttons, forward, back, left, right, to control the motion of the car. And so the car itself has its own processor and a web server running on it, a Wi-Fi web server running on it, and a camera, and it could manage all these tasks. These tasks could be managed remotely. But the idea is that on that car, on this microcontroller, it had to do multiple things at once. Okay, there are multiple tasks that it had to handle. In order to do this, that it had to handle at the same time. So let's look at some of these. One thing is sending video data. So this car, it was constantly, if you were connected to it, it was constantly sending video data from its camera to your phone or whatever your web browser was running on, right? So it had to do that, send video data all the time in the background. Then servicing the motion buttons. So in the interface, you could go to your web browser, hit the forward button, the car would move forward. Hit the back button, the car would move back, and so on. So the car, its microcontroller has to service those buttons. So even while it's playing the video, at the same time, if somebody presses forward, it's got to respond, go forward, go backward, and all that. So it has to do that. Detecting obstacles. So this thing has an auto brake feature, so it has to be constantly detecting obstacles. So if there's an obstacle in front of it, it will brake. Regardless of what the commands are, that will get overridden. So it's got to be constantly detecting obstacles while it's showing its video and while it's responding to the buttons, the control buttons. Also auto brake. So that's another thing that has to happen concurrently. You can be showing video, somebody can be pressing buttons, you can be responding to them. But if you detect an obstacle, you got to brake automatically concurrently with the video and with everything else. So multiple tasks have to be performed by this device. And in a situation like this, it is helpful to have an operating system to handle the multiple tasks, to help you handle them. So what happens is, so I just talking about how they can happen together. You can detect and auto brake cannot occur together, right? So if you detect, then you auto brake. They don't happen together, but everything else can happen concurrently. So in a situation like this, you need to have multiple things running at the same time, multiple tasks being performed at the same time. Now, you could, as a programmer, write a relatively complicated program that does all these things at once and checks, while you're sending video data, it's also checking to see if a button is pressed, it's also checking for collisions and so on. But an operating system makes this easier because you can write each one of these tasks as a separate task and then let the operating system intermix them. So you can write one piece of code that just sends video data, another piece that serves as motion buttons, another one that detects obstacles, and another one that does auto brake. And then you can give them to the operating system, and the operating system will make sure they all run at the same time. They don't have to, as a programmer, you can write things separately. You can write the sending video data code separately from the servicing motion button code, right? And the operating system can interleave them for you, and that relieves a lot of burden from the programmer. So the main job of an operating system is to support a process or a task abstraction. I'm not going to differentiate them too well right now, but let's just talk about processes. A process is an instantiation of a program, so a run of a program. So if you've got a program PowerPoint, let's say, which is running on this machine right here, there's a process. When you're running PowerPoint, it has a process running. And so say on my machine, I open PowerPoint 10 times, right? Then I've got 10 different processes, all instantiations, different instantiations of PowerPoint, right? So a process is like a runtime instantiation, an execution of a program. And you can have many of them at the same time. So the process has to have access to the resources of the processor. The CPU, meaning the microcontroller itself, the memory, right? So a process needs to read from memory, write to memory, and so on. Other resources, the timers, the ADD converters, the network access, all that. The processes all have to access that. But they have to share that, right? So there might be only one ADD converter in this microcontroller, and there might be 3 processes that need to use the ADD converter. So the operating system, part of its job is to manage all these resources, to make sure that everything gets used fairly one at a time. So if all 3 processes want to use this ADD converter, the operating system essentially puts them in a line, says, okay, you were first, so you go first. You're more higher priority, so you go second, right? The operating system's job is to manage all these resources, the memory and the CPU and I/O and ADD converters, all the resources in hardware. The operating system takes care of that, make sure that the different processes can use them in a fair order. Thank you.
Operating system.
Okay. We continue. Quiz. Under what conditions should an integrated circuit be used in an IoT device? Manual power required. All functions are commonly available at an integrated circuit when all the functions are available. When have require low power when all above. Given a choice between implementing a function as an integrated circuit in hardware or as a program in software, what factors need to be considered? The list required time research circuit and the performance required of the final product, the physical look of the final product need to be considered. The list, the physical look, performance required time to design the code, physical look. Generally, in a computer-based system, main memory much larger than cache. 2. What is the fastest type of storage in a computer-based device? Guess. Which statement is false? A programmer may write assembly code barely if performance is very important. High-level language are generally easier to program than yes. Machine language is universal allowing write machine languages can have microcontroller. Assembly code is easier to read than machine code. No. What does an assembler generate? Machine code, assembly code from high level code, machine code from machine code, assembly code from machine code. Combined code generally execute faster than in interpreted code. Combined code generally execute faster than interpret code from with a buffer with compile code generally execute faster compile interpreted code compile. But the following is not a benefit of using an operating system managed program can secure at the same time. The frequency of the microcontroller can be significantly increased. The operating system provides the common program interface to the hardware. Yes. The operating system is able to separate between multiple processes. The frequency of microcontroller can be significantly compiler code very secure, faster compile interface. maybe what fast style storage statement fault. Oh shit. What the right? That's money fault. Okay. Yeah, 4, 5, 6, 7. Okay, 4, 5, 6, 7. Oh shit. This one I will correct. 2, 4. First STIC style storage in a computer by define main memory register and the flash first STIC style register and the cache main memory close flash memory no cache no register. Statement assembly code is easier to read than machine code. Assembly the machine. Yes, high level language. High level languages are generally easier to program in than assembly. Yes, assembly code directly performance is very important. Yeah. What's the assembly assembly machine code for assembly code assembler where assembler code from a high level language maybe this one for lower okay this one there's assembly code from yes maybe 75 so it's very machine combine faster to get on about physical lock to register this one no this one to compile code skill faster than interpreted code voila okay so what will we have here what will we have here research through microcontroller and provide information about them from the internship be sure to include a link to an online reference where you found information research the Arduino and Raspberry Pi platform indicate for indicate if there are operating system we can be beyond its platform. Okay, maybe the way